Welcome to our channel Euclid Mathematics. Today I am here with a very interesting topic and new topic from integral equation. So integral equation, it is the most important subject for a NET, SET and GATE exam also. Because of that, these questions are quite easy questions. Just we can answer them with observations only. So just we need to know some few fundamentals of this subject. So from integral equation subject, we are going to learn our topic, which is a resolvant kernel. In SET exam also, every year they are asking one or two questions. Again, similar for NET and GATE exams. And this is a quite easy point. Here we can answer that question with just an observations only. So here we can adopt two methods that to solve our example. One is I'm having here, which is shortcut method that we can answer very quickly in a second only. And another method, we follow the regular as per given the method of resolvant kernel. Okay, so let's get started our today's video with the resolvant kernel. I will explain how to solve examples by using resolvant kernels and as well by the shortcut method. Okay, so let's get started. Here we have given resolvant kernel as tau of x t lambda. Okay, so lambda is a constant which given in examples. Okay, so tau of x tau lambda x t lambda is given summation n running from 1 to infinity lambda raised to n minus 1 kn of xt. Okay, so here kn of xt is a kernel of a given integral equation. Okay, so and for finding the different k1 of xt, k2 of xt, k3 of xt up to kn of xt, so we have to use the standard formula for kn of xt, which is equal to t to x. Okay, that t to x, its limit totally depend on whether the equation is a Fredholm integral type equation or a Volterra integral type equation. Okay, into kernel k of xz into kn minus 1 zt dz. Okay, so this is the kernel. And by using that kernel, we have to we have to find out the value for kn minus 1 of zt. Okay, that means when you run n different, you will get the value for k1 of xt, k2 of xt, kn of xt. Okay, and that k of xz into kn minus 1 zt. Okay, and we have k of xt as a kernel. Kernel, we know that in the Fredholm or Volterra integral equation, how we define kernel. Okay, so let's here we have the result for that one. And another one we can find directly resolvant kernel by gamma of xt lambda is equal to k of xt into e raised to lambda into x minus t. Okay, I will explain that one later. Okay, now we just have to understand how one can solve this way. Okay, so let's get started with some of the examples. Okay, so it is easier to understand when we solve some examples. Okay, so let's get started with examples. So here first question, to find out a resolvant kernel. Okay, now let's read the question for the integral equation phi of x. Okay, so integral equation is given phi of x, which is called x plus 0 to 1 by 2 integral over 0 to 1 by 2 phi of zeta d zeta. Then we have to find out the resolvant kernel r of x zeta 1 is. Okay, so we have to find out the resolvant kernel, and which one of the option we have to check, which is the resolvant kernel between these four. Okay, now as we observe here, our integral equation, it is of the form 0 to 1 by 2. Okay, so that means a to x. Okay, it might be and here k of xt, it is also k of xt is the part of that integral. Okay, so k of xt, it is not present here, that means it has value 1. Okay, and lambda, it is not present here, that means lambda is also having 1. Okay, so lambda 1, k of xt 1. So as we can see in kernel r of x zeta lambda it is here 1. Okay, so by using this, we have to find out resolvant kernel. Okay, so as we have k of xt, which is a 1. Okay, this is the coefficient here for k of xt, which is a 1. Okay, now let's find out the solution for this example. Okay, so as we can see, for finding k of xt, we use the method for iterated kernel. K of xt is equal to k1 of xt. Okay, so first of all, we have to find out iterated kernel. Okay, once we get the iterated kernel, then we move for the resolvant kernel. Okay, because we need iterated kernel in a resolvant kernel. Okay, so k of xt is equal to k1 of xt, which is a 1. Now we want the kn of xt. That means we have to find out how kn of xt look like. Okay, when n goes to bigger and bigger. Okay, that means when k1 of xt it comes as 1, then k2 of xt how it look like, k3 of xt, then k4 of xt, until kn of xt. Okay, just we have to find out how their n term it's look like. Okay, then it is easier to get the resolvant kernel. Okay, now let's find out k of xt. K of xt is here as a 1. Okay, k of xt is given 1. That means k of xt is a k1 of xt. This is the first form we have to remember here. K of xt is equal to k1 of xt, which is a 1. Okay, and kn of xt, which represent 0 to 1 by 2 integral over 0 to 1 by 2, which given in example. Okay, integral, that value given in our example. So k of xz into kn minus 1 of zt dz. Okay, so we can see that here k of xz and kn minus 1 of zt dz, these are the two new terms. Okay, so we have to build that term by using k of xt. Okay, So let's build this term now. So we have k1 of xt. Now we need k2 of xt. So put n which is equal to 2. So k2 of xt which is equal to 0 to 1 by 2 k of xz, n which is equal to 2. That means k2 minus 1 of zt dz. Okay. So k2 of x2 which is equal to k of xz into k1 of zt dz. Okay. So k of xz, we want the k of xz. Okay. K of xt is 1. Replace t by z. So k of xz, it is also 1 because it is a constant. Doesn't matter when x and t, these variables get replaced. Okay. So k of xt is 1, then k of xz is also 1. So k1 of zt, okay, replaced by x by z, k1 of zt. So that means k of zt means k1 of zt. Okay. So k1 of zt, it is here. K of xt and k1 of xt, it equal. Then k1 of zt, it is also 1 because it is a constant. Okay. So k of xz is 1, k1 of zt also 1. Okay. Into dz. Okay. Now let's go for further integral. So k2 of xt, it is the integral over 0 to 1 by 2 into dz, and integration of a dz, it remains z. Okay. And integral, their limit, it is given 0 to 1 by 2. Okay. So substitute this limit 1 by 2 minus 0, it remains 1 by 2 only. Okay. So I got the second value for our iterated kernel. Okay. First value, it is 1. Second value, it is a 1 by 2. Okay. Now let's find out third value. So third value, it similarly get by using this one. Okay. So k3 of xt which is equal to k of xz. Okay. So k of xz, it remain 1. Okay. It remain 1. k3 of xt here, k of xz, it remain 1. Now again substitute 3 here, k3 minus 1, that means k2 of zt. So k2 of zt, it is 1 by 2 here, 1 multiplied by 1 by 2 into integral over dz. Okay. Okay, let's find out the integral now. So 1 into 1 by 2, this is a constant term, take it out. Integral of dz, it remains z, and substitute their limit. Okay, 1 by 2. Okay, so 1 by 2 multiplied by the value for that integral, it is also 1 by 2. Okay, so 1 by 2 into 1 by 2, it's their bracket 1 by 2 bracket square. Okay. So k3 of xt, it look like 1 by 2 bracket square. Okay. So when k2 of xt is a 1 by 2, k2 of xt is there, we get the 1 by 2. When k3 of xt, we get the 1 by 2 square. Okay. So similarly, we don't have to go for a further value for k4 of xt, k5 of xt, or kn of xt. Okay. Because this is some special type of integral. So it repeats the value as their powers only. Okay. So 1 by 2 square, 1 by 3 cube, 1 by 2 raised to n minus 1. Okay. So when here third element it is here, it gets the power 2. Okay. So k3 has given power 2, k4 given power 3. Similarly, kn gives power n minus 1. Okay. And kn plus 1 gives power n. Okay. So I got the value for kn plus 1 of xt is a 1 by 2 to the power n. Okay. This is only the iterated kernel. Okay. So for finding a resolvent kernel, we need iterated kernel first. Okay. What is the result for resolvent kernel? Resolvent kernel of xt lambda, which is equal to summation n running from 0 to infinity, kn plus 1 xt lambda raised to n. Okay. So lambda, we know that it is having value 1. And 1 raised to 1, nothing matter. Okay. So kn plus 1 of xt, it is here 1 by 2 raised to n. Okay. Now substitute this value in our result. So n running from 0 to infinity, kn plus 1 of xt is a 1 by 2 raised to n, and lambda raised to n remains same. Okay. This one is a standard result which you all need to remember. Okay. This is the result for finding resolvent kernel. Okay. Before we found here the iterated kernel. Now substitute that iterated kernel into resolvent kernel, and resolvent kernel, it says that r of xt lambda is equal to summation running from 0 to infinity kn plus 1 of xt lambda raised to n. Okay. Now substitute this value here, 1 by 2 raised to n. Okay. This one is here, and lambda raised to n remains same. Okay. Take it inside lambda here. Okay. So when we run that summation as a 0 to infinity, we get the value lambda by 2 raised to 0, lambda by 2 raised to 1, lambda by 2 raised to 2, lambda by 2 raised to 3, and plus 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 so on. Okay. So we have the value for lambda which is a 1. Okay. Now it is lambda getting 1, that means 1 by 2 raised to 0, 1. 1 by 2 raised to 1, it is 1 by 2. 1 by 2 raised to 2, it is 1 by 4. Okay. It is 1 by 8. Okay. So we can see that we got some special type of a series here. Okay. Which is a geometric series. And we know that how to find the sum of a geometric series. First term upon 1 minus common difference. So first term, it is here 1 upon 1 minus common difference between all the term. Common difference means we have to divide second term by first term. Okay. So 1 divided by 1 by 2. That means we get the, 1 by 2 divided by 1, we get the common difference. Again 1 by 4 divided by 1 by 2, we get the common difference. Okay. So 1 upon 1 minus common difference. So 1 upon 1 minus common difference is 1 by 2. So 1 upon 1 by 2. So denominator of denominator getting numerator. Okay. So it is value 2. So our resolvent kernel. Okay. With the value for resolvent kernel r of x t lambda, that means r of x zeta 1, which is a 2. Okay. Now let's check out which one of the option is correct from our given question. Okay. So we can see it here. We want the resolvent kernel here, r of x zeta 1. Okay. So we can say that 1 by 2 it is not possible. Okay. 3 by 2 also not possible, and 4 not possible. We got the exact answer as a 2. Okay, this is the way to find out the value for a resolvent kernel. I hope so you all have understood my today's lecture. For similar and more example, you can check it into my playlist. I added more video there. Okay, so thank you everyone. Thank you for my today's lecture.